Hi, I'm Tammy. I'm a master's student at Carleton University, and I'm working with my advisor, Shada Ipek, on this project of baryon asymmetry of our universe, specifically looking at it through the lens of particle and antiparticle oscillations. So we live in a universe that's composed of baryons. So these are protons and neutrons, and then these go on to create larger structures that compose everything around us. However, if we go ahead and measure the antibaryons in our universe, we find that there's pretty much none, which is an interesting outcome given that we typically assume an inflationary model for the early universe. And so even if there were some asymmetric initial conditions, the inflation would have just washed those away. And again, we come back to some symmetric initial conditions where we have equal amounts of particles and antiparticles. However, today we only have particles. So to answer this question as to why we see this asymmetry is what we are trying to answer here. And to quantify this asymmetry, we typically use the parameter eta sub b, where this is the difference in the baryon number density and the antibaryon number density normalized to the photon number density. This gives a value of order 10 to the minus 10, and the way you can think of this number is that if in the early universe you have close to equal amounts of baryons, and when they collide, they annihilate with one another. However, there was this small 10 to the minus 10 number of surplus of particles that didn't find a partner to annihilate with, and so those went on to create the universe that we observe today of only particles. In the 60s, several people started working on this question of the baryon asymmetry of our universe. Specifically, Sakharov had written a paper in 1967 that laid out the three necessary conditions to accomplish this. So the first is baryon number non-conservation. So if we model this with a proton and an antiproton in the early universe, and the net baryon number at that point is just 0. They all cancel. However, today we only have baryons, so let's model this with just one proton with a baryon number of +1. So since 0 doesn't equal to 1, we have a violation of this quantity. The second condition is charge and parity violation, which is a statement that we need to be able to distinguish between particles and antiparticle states. So as an example, let's consider the kaon system, the neutral kaon system, where K0 can decay into the pi plus, the pi minus, the positron, and the electron neutrino. And similarly, its anti-kaon system, kaon particle, K0 bar, can decay into the electron, the pi plus, or the anti-electron neutrino. If Cp was an exactly conserved quantity, then the rates of these two decays should be exactly the same. However, when we measure it, it's actually 10 to the minus 3 difference. And so this implies that nature is in fact able to distinguish to some extent particles versus antiparticles. The third condition is out of equilibrium. So when in equilibrium, you get forwards and backwards reactions that occur quite easily. So within thermal equilibrium, you can generate as much baryon number violation or parity or charge and parity violation as you would like, but those can just be washed away with the backwards reactions. So to quantify this out of equilibrium condition, we use the interaction rate to be falling below the Hubble rate, where it's a function of T, which is the temperature of our universe. So schematically, we can look at this diagram here, where in dark blue we have particles, and in the lighter blue we have our observable universe. So at this time, the particles are quite condensed with one another, and so the likelihood of finding each other and interacting is fairly high. But as the universe expands, these particles also scale with the expansion, and so the likelihood of them interacting now becomes much smaller, and at some point they will fall below the Hubble rate as well, and this is the time at which they freeze out. So the first two conditions, the first two Sakharov conditions, are actually observed within the standard model, but the third condition is not, because standard model interactions are fairly fast and they're always higher than the Hubble rate. As I mentioned, the first condition is actually met within the standard model, so baryon number is in fact violated, and this is a result of the fact that we have chiral fermions. So left-handed and right-handed fermions interact differently with the weak interactions. Specifically, the right-handed fields or particles don't engage with the weak field at all. And as a result of this, we end up seeing these currents J mu L and J mu B, where L and B are lepton number and baryon number respectively, are the four derivatives of these currents are non-zero, in contrast to conserved values where you would expect them to just equal to zero. So what this is saying is that within the standard model, we in fact do have B plus L number that is getting violated. However, this is highly, highly suppressed at low temperatures, and this is why we don't see proton decays, for example, within the lifetime of our universe. However, at high temperatures, so between the ranges of 130 GeV to about 10 to the 12 GeV, these processes are actually quite rapid and they occur frequently. And so this process is done through something called the sphalerons process. So the sphalerons are able to violate this B plus L number between those temperature ranges. And so the problem, though, is that the sphalerons are in equilibrium within those temperatures, and so this B plus L number generated can always just be washed away through the sphalerons process as well. But what's interesting is that if we include a number B minus L, then the sphalerons are actually blind to this quantity. So you can generate this B minus L and it will continue on through the evolution of our universe. But in order to incorporate this, you would need to have some beyond the standard model physics as well. So the second condition is CP violation, and just like the baryon number violation, it is actually present within the standard model through the CKM matrix. So in this matrix, we have an irreducible phase that produces the CP violating effects, and we've observed this through neutral meson systems, for example, the kaon system. So the kaons, these neutral kaons, engage in these box diagrams that allow for it to oscillate between its particle and antiparticle states. And through these oscillation modes, or these kinds of processes, we end up seeing the CP violating effects. However, the problem is that although we do see this CP violation within the standard model, it's far too small to explain the vast amount that we observe for the baryon asymmetry problem. To explain what we observe, we introduce our model where we work with a pseudo-Dirac fermion composed of two Weil fields, eta and chi, where we define our pseudo-Dirac fermion to be this psi particle. So if we write out our mass Lagrangian, we see that we have our usual Dirac mass term defined with capital M, and then we also include these small Majorana mass terms, m chi and m eta as well. And once we introduce these small Majorana masses, we end up breaking this global symmetry as well. If you then compute the eigenvalues of this system, you end up finding that you have this oscillatory behavior that goes between your particle and antiparticle states, very similar to the neutral kaon system. And so what this means is that if we start at some initial time with our psi particle state and let it evolve in time, you will end up getting this psi c component, the antiparticle version of it as well, where there's some amplitudes that are associated with it that are different from one another. So schematically, we can observe it through this diagram, where in pink we have our psi particle, and then in blue we have our antiparticle psi c. And so let's say at initial time t is equal to 0, we have 100 psi particles and 0 psi c particles. Some of them will oscillate into the blue and vice versa, and so you get this oscillatory behavior. But in the early universe, these particles, these psi particles, are decaying, so you get this damped oscillation pattern as well. Now, to be a little bit more concrete with the math that I just spoke about, we can write out the Hamiltonian of the system, which is the difference between our mass matrix and our decay matrix. Where our mass matrix, the diagonal terms are the Dirac masses, and the off-diagonal terms are the Majorana mass terms. And then in our decay matrix, we have G chi and G eta, which are the coupling constants of our chi and eta fields. We can always rotate away any complex phases that are present in our mass matrix and push this all into our decay matrix, which will lead to a CP violating effect because of this irreducible phase that we've pushed into the decay matrix. So you can then write out the system of equations that come out from applying the Hamiltonian on our psi particle state, and you find the difference in our eigenvalues defined by gamma or lambda plus and lambda minus. So these are the two different eigenvalues. And again, we define our delta m, the mass difference, to be the real parts of this eigenvalue difference, and then the imaginary components to be the difference in our decay width. So another, as I mentioned, a key feature of our model is CP violation. It's one of the necessary conditions to be met. And so we define CP to be, or CP violation to be this epsilon parameter, which is the difference between the decay width of our psi particle decaying into a lepton versus it decaying into an anti-lepton. This is also summed over our psi c particle going to a lepton and psi c particle going to an anti-lepton. You can solve this numerically, but you can also find an approximate solution where we see that it's a function of this thing x, where we're defining that to be the mass splitting divided by our decay rate. And then r is the ratio of our coupling constants g chi and g eta, and phi is that irreducible phase that we pushed into our decay matrix. So if you plot this out with respect to x, you see that CP is maximized when the mass splitting is of the same order as the decay width. Now let's consider what's really going on in the early universe. At earlier times, particles are not only oscillating, but they can also scatter off of each other and annihilate with one another. And then we can write out the Boltzmann equation that encaptures all of these dynamics given by something that looks like this. In addition to this Boltzmann equation, we can write out the interaction Lagrangian, where our psi particle can either scatter off elastically from a very light fermion denoted by F, or it can annihilate with each other and annihilate into these light fermions. You can then write out the cross-sectional areas for both the annihilation and scatterings. And from that, we can then create a plot that shows the rates of these kinds of interactions. So what's important here to consider is the relationships of when things freeze out, when our interaction rates freeze out. So if our expansion is much greater than our interaction rate, then your particle will no longer be able to find a particle to scatter off of or annihilate with, and so that's freeze out time. So schematically or graphically, we observe it at the intersection points between the Hubble rate in this mauve color and the annihilation rate here, and likewise for our scattering rate, where this below this point we end up getting frozen out interaction rates. Another important thing that we're considering is oscillations of our particles. And so we find that particles can't proceed to coherently oscillate until the interaction rates, the annihilation and scattering rates, fall below our oscillation frequency, which we define to be 2 times the Majorana masses. And so similarly, we're looking at those intersection points. So where this blue curve converges with this purple line, and same thing for the yellow coinciding with this purple line as well. So from that Boltzmann equation I showed from a couple slides ago, we can define this parameter delta, which is the asymmetry of our psi particles. So here Z is our x-axis again, and we've set our initial conditions to be 0. So initially we have equal amounts of psi particles as well as psi c particles, and with time it develops an asymmetry, and at finally when annihilations freeze out, you can then get this coherent oscillation pattern we observe. And in different colors we see that the larger the energy scale, the greater the asymmetry that can be formed. We can also plot out the total psi particle yield given by sigma here, where we see that the overall shape is this decay envelope. However, for each curve, we also observe this kink. And this kink is approximately when the annihilations of these particles freeze out. In different colors, we've shown the different masses of our pseudo-Dirac fermion. And as expected, you see that the larger mass range has a smaller yield because those are more Boltzmann suppressed than the smaller mass ranges. So as I've shown in the previous slides, we've developed a particle asymmetry, our psi and psi-c asymmetry in red. We've also shown the total yield of our psi plus psi-c's, but we also are interested in the decay products of these psi particles. Specifically, we're interested in the lepton asymmetry, which we've plotted in green. So this is the difference between our lepton number density and our anti-lepton number density. And to capture this, we've included this differential equation, where again, this epsilon parameter is our CP violating parameter. And this equation just captures the decays of our psi's that decays asymmetrically into our lepton particles. Schematically, if we picture it, we have a psi particle in blue here that decays into our leptons in green and anti-leptons in yellow. So from this, we've developed a lepton asymmetry. But we can't just end there. What we really want is the baryon asymmetry of our universe, and so somehow we need to convert this lepton asymmetry into the baryon asymmetry. To do this, luckily we have that sphalerons process that I mentioned earlier on in this presentation, where through careful detailed balancing of chemical potentials of the leptons and the baryons, we can convert a fraction of our lepton asymmetry into the baryon asymmetry. So it takes a part of this, and we've now developed a baryon asymmetry. So from that, we can show the total parameter space of when we develop the baryon asymmetry of our universe. Specifically, the contours of this plot show us where we develop exactly enough baryon asymmetry for explaining what we observe. And then within the shaded regions, we have an overproduction of the baryon asymmetry. And then in pink, we have a decay rate of 10 to the minus 6 eV, and in blue, we have a decay rate of 10 to the minus 7 eV. So as expected, a slightly larger decay rate produces a larger landscape of parameter space because we can decay at a larger rate into the desired baryon asymmetry. So in conclusion, we in fact do not live in a universe that is composed of both particles as well as antiparticles. We live in a universe that's only composed of baryons. And so hopefully I've been able to show us that using a pseudo-Dirac fermion that oscillates between particle and antiparticle states, we can enhance CP violation, and from that, it's out of equilibrium decays, it can produce a lepton asymmetry, which then is recycled into the baryon asymmetry using the sphalerons process. Thanks for listening.